In this video we will be looking at the non-deterministic finite automaton, section 1.2 in Michael Sipser's book. But before we start on section 1.2, let me review with you what we have done in section 1.1. In deterministic finite automata we have learned some notations. For instance, we've learned that to draw a state diagram like this for a machine, and then we've learned that when we have states like this, we have an initial state, and the initial state always starts with a little arrow pointing toward the initial state, and then we also have a final state, and the final state is double circled, and we have edges. In this state diagram we have an initial state Q1. If this Q1 accepts or reads a 1, it goes to Q2, and if it reads a 0 from Q2, it goes to Q3, and if it reads a 0 and the initial state, it goes to itself, goes back to Q1, and if it reads a 1 on Q2, the second state, it will go back to Q2, and then if at Q3 reads a 1 or a 0, goes back to Q2. We also learned the formal definition of a finite automata, and that is consists of the five tuples are the Q, which is the finite set of all states, and I'll explain all of these in a minute, and then the sigma, which is the set of the finite alphabet, the transition function or the transition matrix Q cross sigma, and the output will be a transition state, and I will explain this also, and then Q naught, the initial state or the start state, which, as I said earlier, the start states with always having an arrow pointing to it, and then the final state, and the final state must have the acceptance state for the language to be recognized, and in this case the acceptance states is Q2. So let's apply these five tuples to this example that we see in front of us here. So in this diagram that we see in front of us, the Q, in this case the set of all transitional states, is Q1, Q2, and Q3. These are the states Q1, Q2, and Q3. Sigma in this case is the alphabet of the tested two strings are 0 and 1. Incidentally, why you have three states here? Because these three states based on the length of the string, which is in this case is 2, so that's 2 plus 1, and that's 3. That's why you see three sequential states here. And then the Q naught is Q1, and the final accepted state in this case is Q2. Now the initial state, you see it with an arrow pointing to it. That's how we do it in the state diagram, and the acceptance state is a double circles. So the acceptance state is this double circle, and the Q naught or the initial state or the start state is that little arrow that you see there. Now we are going to do the transitional matrix or transitional function, and that we will do it, my friends, this way. Every book does it differently, but we are going to do it this way. We're going to follow the book, and here we have the delta, and delta is all the possible states, in this case Q1, Q2, and Q3. And here is the alphabet, so we have a 0 and 1. Now we are going to apply the string or the word that we want to test for this machine to be accepted by this machine or not. and we do it. Let me change the color. So we're going to look at every single character and apply it to this diagram. So if the machine reads at the initial state 1, it goes to Q2. The initial state again is a Q1. And if the machine at Q1 or the initial state reads at 0, it stays in Q1. If the machine in this case reads Q2 because it's tangential, so we're going to go to the next state. If it reads a 1, it goes back to itself. This is a Q2. And if it reads at 0, it goes to Q3. And then if at Q3 reads a 1 or a 0, goes to Q2. Now, by the way, this is 0, comma 1, and instead of doing two edges, one for 0 and one for 1, we just like simplify it this way, 0 and 1. Now, and then what we do an arrow like this pointing to the start state and asterisk for the final state. So if this language is accepted, we say the machine is accepting or recognizing the language. If not, we can say reject. So it's always the final state a reject, accept, or reject. So that's basically what section 1.1 is, and we've done examples in the class. Now let's move on to the new material. In a non-deterministic finite state, given a current state, there may be multiple exist states. Giving, let's say you're at Q naught, reading any symbol, you might go to Q1. The state might go to Q1, Q2, or back to the initial state. So there may be existing many paths in a non-deterministic finite state. How do we execute a non-deterministic finite state machine? We can look at them at two different ways, and they are both the same. We can imagine that we're choosing the next state at random, or we can have some hint that tells us where the next state is, where to go to, basically. Or we can select all the next states to go to in parallel, simultaneously. Now this is a complete different from the deterministic finite state as we saw in section 1.1. In a deterministic or determinism in a finite state, given a current state, you can know what is the next state. So if you're at state A, you know the next state. When you read the string, you're going to a state B. Only one unique path. You can't reading a string 1. If you're going to state B, you cannot have a string. Cannot read a string 1 and it takes you to another state. So only one unique state. No choices and no randomness. So that is the first part, section 1.1, the deterministic finite state. How about modern computers? What are they, NFA or DFA? Well, let's see at classical computers. They have memories and disk and CPUs and registers and many other parts, and they are finite. So there are number of bits and finite number of bits. But if we look at the modern computers are actually they have various sources of randomness, from the quantum effects of transistors memories, materials, fatigue that can happen with inside the box. And so we can say modern computers are a good example of non-determinism, because we can't really guess errors. You have a random errors that can happen, and we can't know what's the initial state of this randomness. So modern computers in general, they are non-deterministic finite automata. And this is another thing I want to introduce to you to it. This is how we notate the non-determinism. It's NDF or NFA. Enough introduction, and let's do some examples. In a non-deterministic machines, now we allow multiple edges with the same label. So let's say you're at the initial state, or at this state A, and you get a 0. Do you go to state B, or do you go to state D? So do you go here, or do you go to this state? And let's assume that you got an A. Do you have let's assume that you're in a state A and you got a 1. Do you stay in state A, or do you go to C? So what's the choice? What is the choice that we need to take, or this machine will take, to get the final accepted state, or this language will be? What's the choice? We also are going to allow something called Epsilon Edge. An Epsilon Edge is an edge labeled with an empty string, or the epsilon symbol. Normally we use the symbols from the alphabet, and that's in the deterministic finite state. But in non-deterministic finite state, we accept epsilon edges. So you can take an epsilon edge without scanning a symbol, so you don't have to scan a symbol. So if we're in state A, we can scan a 1 and go to state B, or we can scan a 0 and go to state C, or we don't scan 1 or 0 and go to state D and or state E. And maybe from these states we have another transition that can take us to another state. So it's for the D or E. So we can take these epsilon edges. It is an optional edge. Here in this example, we want to recognize a string that contains 0, 1, 1, 1, 1, 0. Should be accepted and recognized as part of the language. So it's very straightforward to build a machine if we have a non-determinism. So if in this case, if we have a 0, 1, 1, 1, 0, we are at the initial state. If we read a 0, we go to state B, and 1 we go to state C. If we read 1 on state C, we go to state D. If we read 1 on state D, we go to state E, and then from E we go to F, and then that's the acceptance state. The state G is the acceptance state. So as I said at the beginning, when I looked at this example with you, if we are at state A, the initial state, and we get a 0, we can go to B or stay on A. So, but as you can see that I just selected the right path, or the correct path, correct acceptance path right away. But what if this is not clear to us? Because in a non-deterministic finite automata, for each state there can be a 0, which is in these cases here 0, or it can be more options, so it can be 2 or more transitions corresponding to a particular symbol. And also in a NFA, the state with the more than one possible transition, which is this case here, we can branch it. We can branch it to other states But again, as I said, in this example, it was so clear, and so we selected the right path. So there is another way of, instead of guessing, there is another mathematical or scientific way to do the non-deterministic finite state, which is we use trees, and we call them, your book calls them trees of possibilities. They're also called computation trees, and they also called the choice tree. So in the next example, and it's from your book, we'll look at an example. We will look at an example that it can use the benefit from the trees of possibilities. So let's use this finite machine as an example. You can see there is an epsilon edge, so therefore you know this is a non-deterministic finite state machine, and there are two edges of 1 coming out from the initial state Q1. So now let's test our string with this machine. So if we're reading a 0, we're staying in a Q1, and if we read a 1, we can go to Q2. We read another 0, we go to Q3. Q3, we read a 1, we go to Q4. We read a 1, we stay in Q4. We read another 1, we stay in Q4, and then another 0, and so therefore this is an accepting state. So what we need, only one path to an accepting state. Are there other choices in this case? So the answer is yes, by using computation tree or choice tree or tree of possibilities, as it's called by these three names. So let's look at the same problem again using the trees, and just remember that epsilon is a choice that the machine can scan. So epsilon is empty string, and we have an epsilon here on an edge, epsilon edge here. So if we scan, and here's the values, I have them here, and also here are the values, so let's just like keep track of them. So let's see, the first one is 0. So if we have a 0, the only choice we have with 0 is to stay in Q1. And if we pass a 1, if we scan a 1, which is our second value, then from 1 we can stay in Q1 or go to Q2 or or scan an empty string and go to Q3. The next number is 0, so if we are at 0, so we go from, the only choice for 0 is to go to Q1, okay? And if we are on a Q2 and we scan for a 0, we go to Q3. Now the next value is 1, so if we scan a 1 on Q1, then we go to Q1 or we go to Q2, and if we pass an epsilon, we go to or if we scan nothing, epsilon is an empty string, epsilon is an empty string here, we go to Q3. And now the next value is the 1 here. So if we scan a 1 from Q1, we go to stay in Q1. If we are in Q1 and scan a 1, we go to Q2. If we do an epsilon, we go to, if we scan nothing or an empty string, we go to Q3. And then from here, this is a dead state, and so is this one is a dead state, and so is this one is a dead state. And finally, if we scan a 0 from this branch, we stay in Q1, or if we're in Q2, we go to Q3, and these are also dead states. Now if we scan a 1 here, or if we scan the 1 here, we go to Q1, 1 here, we go to Q2, and here if we scan nothing or an empty string, we go to Q3. If you are at Q3 and we scan a 1, we go to Q4, and from Q4 we go to the acceptance state, and from here we go to the acceptance state. And you can follow this example in your book, and you can see with the tree we discovered 2 paths that are recognized by the machine. Now here's the formal definition that you see in page 53 in your book, and it's same as the four parts of it are the same as you've seen before in the formal definition of deterministic finite state. The difference between them now is this transitional function, and also remember that we can in a non-deterministic finite state machine, the machine can scan empty string, which is we denoted by epsilon, right? So sometimes I write epsilon like the member of, but it's not member. This is epsilon. So let's go through them one by one. Again, this is the same as before. Sigma is the alphabet, 0, 0, 1, or AB, and then the Q is the set of states. The Q set of states, you minimum of 2, and then the Q naught, or the initial or the start state, is member of the Q states. So this is a set, part of the set of the Q state. And then you have the final state. The final state is a subset of the Q, so you can have one final state or multiple final states. And then we have the transitional function, or my old math books they call it transitional matrix. And now this is a little bit different than this is different than the deterministic finite state, because it's power of sets. So remember, on the deterministic finite state, if all states, if we know the initial one, there is a unique transitional state as the scanned whatever the alphabet can go to. But on the non-deterministic finite state, we can go to a 0 or multiple states. So this here, it says that knowing Q, or given Q state with a string, with a character, with an alphabet, the transitional function can tell us which set, and put under set a line here, because it can be more than one set, okay, or a 0 set, or it can tell us which sets of states we are going to. But in a minute or two, maybe I will review the power set for you. I know most of you have that in a math course before, part of the prerequisite for this course. But I feel like at this case, at this time, I need to maybe explore this with you, because that will help you on the theorems and the proofs that you see starting on page 55. So for us to understand the transitional function in the non-deterministic finite state, is we need to remember what are the power sets, which they are by definition the sets of all subsets. And the power set is a function. It takes in its argument the set itself. So for a set ABC, my example here, you can have an empty set, or A, or B, or C, or AB, or AC, or AB, or BC, or ABC. So the number here is 2 to the n. N in this case is equal to 3. And so that's 8 possibilities. This n can be a large number. Again, this an empty set can be donated as such, or you can use the phi symbol, that's this Greek symbol that we use for it. So now what's the relationship between the power sets and this? And if you look here, let's assume that here's the finite state, the undeterministic finite state, and you always now recognize this by using the by seeing the epsilon here. So if we're in state 1, okay, we can go to, and we scan an A, we can go to 4, or we can stay in 1, or we can go to 3, and if we scan an A again, we can go to 2. If we scan a B, we can stay on 1 here, or go to 2, or go to state 5. If we scan an epsilon or empty string, we go to 4 and from 1, or we go to 3, or we go to 5. So if we scan an A, we go to state 1, 3, 2, or 4. If we scan a B, we go to state 1, 5, or 2. And if we scan an empty string, 4, 3, or 5. So keep this power set idea in your mind when we start building the transition function for non-deterministic finite state. So we're visiting this example that we have done before. So Q on this case is the set of Q1, Q2, Q3, and Q4. And the alphabet 0 and 1. How do you know that? You can see that in here clearly. And then the initial state, or Q naught, is Q1. This is the initial state. And the acceptance state, Q4. And now the transitional function, or the matrix function, the delta. All the set of the states Q, which is all of those here, and over the one of the alphabet 0 or 1, the power of the set Q. So here is the matrix table. This is delta, and these are the alphabet 0, 1, and the empty string. Empty string is always part of the non-deterministic finite state. So if we are at Q1, we have the option to scan Q1. And we scan 0, we can stay on Q1. Okay, and if we are at Q1 and we scan a 1, we go to Q. We stay in Q1 or go to Q2. If we are on a Q1 and we scan an empty string, we go to phi, empty state. Remember, empty state is part of the power Q. And then if we are in Q2 and we scan a 0, you can see we go to Q3. If we scan a 1, we go to phi. And if we are at Q2 and we scan an empty string, we go to Q3. If we are at Q3 and we scan a 0, we go to phi. Phi, remember, every state can have multiple of states, or 1 state or 0 state. And if we are at Q3 and we scan a 1, we go to Q4. If we are at a Q4 and Q3 and we scan an empty string, we have an empty set. And so if we are at Q4, we scan a 0, we stay in Q4. Forgot the 0 here. And if we are at Q4 and scan a 1, we stay in Q4. There should be a 1 here. And if we scan an empty string, we go to a dead state, or phi, empty state. This is an example from your book. I went through it, I think, multiple slides now.